this six-page paper is the best I ever wrote if you measure it in order of ideas per byte. So, so if anybody wants one of those reprints, they're there. I've also got here 6 copies of the MMIX documentation as it stands today. There's only 6 here, but it's downloadable. Anybody can, if you click on the home page, you can get the postscript for it. But if people here are really seriously promised to read it closely and report errors to me, I have 6 here, and if they're gone, then you can download. I found one error in it this afternoon, but anyway, there it is. And also, one more announcement. Next Friday, a week from this Friday, I'm going to give another lecture in this room. It's not in the computer musing series, but it's a different thing. It's about digital typography, and they tell me that my book called Digital Typography was printed last week in Winnipeg. At least the ink went on the paper last week. And theoretically, the copies will arrive here either next Thursday or next Friday in time for this lecture. And I plan to show the book at that time and see it probably for the first time myself. It's a book that summarizes everything I did about on tech and Metafont and other things like that over the last 20 years. And I think it's a lot of fun to see this all in one book. Okay, that's the end of my announcements. I'm going to talk today about this thing. You see here, MMIX, a Risc machine for the new millennium. Now, I guess the first thing I should show you is this cartoon, which I saw here, which says, the mayonnaise for the next millennium, chips for the car for the next millennium, the toilet paper for the next millennium. It says 1999 is going to be a long year. That's probably true, but I think in this case, my MMIX has a little bit of a reasonable claim for this title because the M stands for millennium. I mean, each M in MMIX stands for 1,000, and so and as we'll see. What? I got one more graphic here to show you. Yeah, the happy hour. Now, I think most of you probably know that there was a computer, that still is a computer in my books, The Art of Computer Programming, called MMIX. And I brought the new edition of The Art of Computer Programming here to show you where MMIX is defined, because we can see on page 124 the new, Allison, can you, that's great, wonderful. Okay, so you see this little construction symbol here. This is part of the Art of Computer Programming, still under construction. In fact, this MMIX represents the very last hurdle I have to get out of the way before I can really grind out volume 4 at speed. So it says, it must be admitted that MMIX is now quite obsolete. It will be replaced in the subsequent editions by a new machine called MMIX, the 2009. MMIX will be a so-called reduced instruction set computer with RISC, which will do arithmetic on 64-bit words. It will be even nicer than MMIX, and it will be similar to machines that become dominant during the 1990s. The task of converting everything in this book from MMIX to MMIX will take a long time. Volunteers are solicited to help with that conversion process. In fact, that's one of my main goals today, is to try to see how many of you in the audience I can convince that you would love to join this volunteer effort. Meanwhile, our author hopes that people will be content to live for a few more years with the old-fashioned Mix architecture. Is still worth knowing because it helps provide a context for subsequent development. Well, this was the old machine Mix as it was, and it was designed in 1963, and I think it still looked fairly reasonable in 1973, and we even had a working meeting of MUG, the Mix user group, where we all had mugs and stuff to celebrate in those days. And But in the late 70s, people started using reentrant coding more. Memories got huger and huger, and the VAX came out, and machine languages started to look very baroque. You couldn't enjoy programming them anymore. And so anyway, but now MIX is totally different from the machines that are out there, and so I knew that that it was becoming more and more of a sore thumb as time went on. That's why I'm doing this now. I've got a web page about it, and I suppose a lot of you have seen the web page because I checked this afternoon and there were 18,000 hits on it. So it tells about something about the background of it. Before I forget, I have to show you this about the name. Excuse me. I've got to talk about this trivial stuff before I get into the deep stuff. It always helps. Well, remember, MIX was the 1009, and the reason was that it was the 1009 is if you took these computers, the 360, you heard of that? 650, that was 650 was the one I learned on, 709, and all these things, the U3, we call it UNIVAC, 3, solid state 80, and all these machines, including the II, which people have misread as an 11. That's actually not a PDP 11, it's a recomp 2. But anyway, you add these numbers together and divide by 16, you get 1009 was the average of that. So now MIX is the world's first poly-unsaturated computer. And when this book has been translated into many languages, and the translators in Russia wrote to me and said, well, how do you translate poly-unsaturated into Russian? And I said, it's totally anti-revisionistic. The point is, it was some buzzword that somebody on Madison Avenue would be able to say. Now, I don't know exactly what I'm going to say about MMIX here. If you've got a good idea for how to replace the sentence, let me know. But John Hennessy and Dave Patterson came out with the second poly-unsaturated computer in their book on computer architecture, and it's called Deluxe, DLX, and that's 560, and they found how DLX was actually 560 you could get by this calculation. So I had to prove this too, and so the 2009 is here. It comes from Cray 1, IBM 801, Risc 2, Clippers 300, AMD 29K, Motorola 88K, IBM 601, Intel i960, Alpha 2164, Power 2, MIPS 4000, Hitachi Super H4, StrongArm 110, and the Spark 64. You add all those numbers together, divide by 14, 2009. It had to be 2009. There was a dance group at Stanford, at Tressiter, not Tressiter, at Dinkelspiel a few years ago called MMIX, but I actually found out that that MMIX, MOMMIX, is a popular dialect word in Ozarks, and it means to screw something up. I mean, so anyway, there's a lot of reasons to have a computer called MMIX. But maybe you should do like Tech and say MIX. I don't know. Now the web page also has a defense as why have a machine language at all, and people don't really spend much time programming in assembler anymore, so why should I harp on it? And I explain all these extremely important reasons why I believe that in a series of books like mine, it's important to have some kind of a model that's realistic to base things on. Instead of just working from top down, I like to also work bottom up, and so I discuss the ideas here. In fact, the high level languages keep changing, but at the low level we can have some understanding of what's easy to do on a machine and what isn't. And there are quite a lot of reasons, and they're summarized there. I don't want to spend the time right now, Let me see, what other handouts do I have here? Yeah, I'll get to those. So, but basically, I want to have some a machine language which is actually very much like the most machines in some way. Now, what other criteria did I want for this language? I should also say that the very first time I ever gave a lecture called Computer Musings was almost exactly 7 years ago, and I talked about MMIX at that time. That was my first computer musing was called MMIX, a Risc computer for the new Millennium, and I had just read half a year before that, a few months before that, Hennessy and Patterson's first edition of their book on computer architecture. Speaking of the devil, it's just a phrase, John. It's just, and at that time, John very graciously looked at the entire document that I had about what I thought MX would be in 1992, and made extensive comments. And his main comment at that time was, it's got to be 64-bit machine. At that time, essentially every computer was, I don't know, I had the idea that, okay, I had to go down from 36 bits to 32 bits, but I was never going to get any more. Unix seemed that an int had to be 32. I mean, but machines were coming out 64, and he was absolutely right. And so that impacted very heavily on the design. Now after the second edition of Hennessy and Patterson came out, my new design is very heavily influenced by that. I also want to give a special thanks to Dick Seitz. Is he here? No? Okay, well, maybe he'll show up in a minute. Anyway, Dick, who was designer of the Alpha chip, worked with me actually on the first mix when he was a freshman at Stanford. He and I worked on the simulator for the first mix, which was in 1970, and published a CS report about that. And then now he's spent a lot of time with me this last year with the design of MMIX. So first of all, I learned from Hennessy and Patterson's book that about Risc machines, the concept of reduced instruction set machines, which originated in many places around the world, but I think a lot of credit goes to Stanford and Berkeley projects that came out about 1980-81, and also some independent projects at IBM and other places. The wonderful thing about the Risc machine is that it's actually can be nice to read the machine language coding. This was not true of a lot of the later machine languages that came out. But all of a sudden, hey, there was a window in time when machine language was fun again, and it'll probably go away, as people have to I don't know, these very high, very long instruction word languages and so on they're going to come out with languages that are again never to be seen by a human being, but we're still at a time when almost readable instructions are going on in the machine, and that was great news for me. Anyway, I wanted to be realistic. But I also had to be sort of I don't know, how do you say it? Well, what does realistic mean? In some ways, it has to be economical. But if I made it economical for now, according to Amdahl's law, it would be wrong very soon. Because computers are everything is changing so fast. And so I figured I better design this thing so that it, instead of looking for what I have now, but I better say what will I do if I can actually make the machine 10 times, put 10 times as much on a chip now, or 100 times as much on a chip, and so on, so that this isn't going to look like it's too much mired in the past by the time I actually get to finishing my book. And so I had to be a little bit ahead of time in this design, or try to predict trends in some way. But I wanted to be something that could be buildable, assuming present trends continue. Although maybe we couldn't build it now. I don't have a realistic expectation that anybody will actually ever build it, because that costs millions and millions of dollars for all the stuff, But I still wanted to design one that I would really like to own, and wouldn't it be great if somebody would actually build it someday? Now they'd have to probably spend a few more millions of dollars just for patent rights to some of the ideas I'm stealing, because I haven't been paying attention to the things in MMIX that are everything's patented nowadays, unfortunately. But anyway, I think that I wouldn't feel right if it was just only a textbook computer that couldn't be built, and that didn't go into into all the issues that you have to worry about in a real machine, like what happens when the power fails, and how do you exactly what happens on an interrupt, and how do you convert virtual addresses to physical addresses, and there's a lot of messy things that have to be handled. And so I studied as much as I could about the machines that are in use now, and I tried to take the cleanest aspect of the thing. So another thing was I wanted to be clean and nice. I didn't want to have it look like it's designed by a committee, because it's designed by me, and I have a chance to I don't have to satisfy anybody else. So I wanted to have the nicest, in some way, thing. I wanted it to be easy to learn, because that's the main purpose of it, is so that I can describe it in my books, and somebody can look at it and they got the idea pretty fast, and they don't have to dwell on it if they're not going to write that many programs in it, just so that they get the idea in mind of what a Risc machine is like. I figure maybe 1% of the people who look at MMIX are actually going to write a program for MMIX, so I got a design for the 99%. Still, I want those 1% to really be happy, and that's the other thing, is fun. That is, it'll be a pleasure for people who do want to spend more time on this machine to do it. There's a lot of advantages to a machine-independent machine. Everything is changing so fast in the computer world these days. It's nice to have a few things that last for a little while. And so by having a machine like this, it's conceivable that we'll be able to do various modeling experiments and so on. That'll still make sense over a period of time. But I can't afford to change my books every time a new trend comes along, and I'm already 61 years old, and I got lots to do, and so I'm trying to write about timeless truths, things that are always important. So I want to have one machine that will stick and stay the same. Although it still is adaptable to many different configurations, and so you can have, even though it's a hypothetical mythical machine, there are cheap versions of the mythical hardware and expensive versions of the mythical hardware. I'm going to be giving a talk on Wednesday, March 3rd, will be the next Computer Musing, where I talk about the simulator that I'm building for MMIX. I was heavy into debugging it yesterday, and I got it to interrupt for the first time on Sunday. This simulator shows how MMIX can exist in infinitely many configurations as to all kinds of combinations of functional units and caching and every buzzword I've heard of. Has a way to describe in MMIX. Well, I don't know. I might think of other parts of the design, but in general, I wanted it to be a combination of all these things, and I came up with this design that I'm going to show you today. Now the first thing is simplicity. This was the same as I had in 1992. Every instruction has 4 bytes to it. The operation code X, Y, and Z, and the operation code. So there's 256 operation codes, 256 X's, 256 Y's, 256 Z's. The typical instruction might be this one, 32, 1, 2, 3, which means 32 means add, and this says set register 1 equal to register 2 plus register 3. So this is typical of a Risc machine to have like this kind of a three registers mentioned in an instruction. One register is the second register operated on with the third register. Now the thing that's fairly different, however, is that there's 256 registers. That makes it, however, as I said ahead of time, because we got to figure out something to do with the larger chips, but also easy to learn because here you are, all these bytes are very simple. In fact, I believe that having a lot of registers is extremely good for compact programming because a lot of my programs, a great deal of the stuff will live in registers all the time and never appear in memory, and this saves a lot of space when you're trying to refer to the numbers that you're working with. So so having a lot of registers has a lot of advantages. Now it has disadvantages too, because if one of the disadvantages is that when you're swapping from one job to another, you have to save the state of the computation. And so what if the job isn't actually using very many registers? You don't want to have to store 256 registers into memory and then load them again when you come back. Well, I've taken care of that too, as we'll see. Let's see. The op, I said, there's 256 ops, and this is and so now let me show you this chart here, which is near the end of my report. In fact, I have an extra copy of it. I'll just put it over. I'll just put it here. These are the. Can you zoom back a little bit? Yeah. These are the 256 codes that exist. I guess I kind of like to have a T-shirt that has this on it because anyway, these are the. So you see that in hexadecimal it's 00 through FF, I won't go through all of them with you this afternoon, but I'll give you the idea. They fall, although there's 256. That's a lot. If you ever have to try to address 256 Christmas cards, you'll know what I mean. But they fall into about a dozen easily remembered categories in the patterns, and what one of the things that I want to stress is the cleanliness of the design, or the sort of the orthogonality of the design. That the things that are true about one instruction are generally true of all instructions. So, for example, in this format, the instructions usually have this form where the X and Y and Z are independent, but sometimes Y and Z are tied together. And so you have, a 16-bit something or other. And sometimes all X, Y, and Z are tied together as one 24-bit field. So you have essentially 3 formats of instructions where all the bytes are independent, or where Y and Z are tied together, or where X, Y, and Z are tied together. Another thing is a lot of these instructions. If you okay, Allison, you can zoom in. You can zoom up again now. Maybe your name wasn't Allison. I've forgotten. Whoever you are on TV, can you zoom up? Yeah. Now, for example, the very first instruction is 00 is called trap, and this is in general. It's sort of an extensive. It's a forced interrupt. It means I know I want to call the operating system. I know I want to stop on this. And here you could make that to any extent. The operating system could do any instructions it wants on that. The very last one, all ones, is trip, which is different. This is an interrupt too, but but it doesn't go to the operating system. It goes to you. And user programs can write their own handlers for trips, while the operating system writes the handler for the trap. So every program has its own interrupt, but don't let the operating system know, which could be used, for example, for breakpoint debugging and various things. And usually, if something's wrong with the hardware, you get either all zeros or all ones, and so one of these things will happen, and you'll know about it pretty soon. I told you about the add instruction, which adds, register Y to register Z and puts it in register X. There's also an add immediate, and that's what this bracketed I means in all these things. And you see. Essentially, every instruction that can that makes sense to have an immediate does, which means that the 256 almost gets divided into half, 128, because you have add and add immediate, where add immediate says instead of taking register Z, you change the opcode from 32 to 33, then it would say take register 2 plus 3 and store it in register 1. Okay, so that's the idea of an immediate instruction. And all the immediate instructions take this Z field and treat it as an unsigned constant, and works like that. So just by learning the rules of immediate, you learn a whole bunch of more. Now the add instruction has both signed and unsigned variants. So add and add immediate. Then there's of course subtract is for subtraction. There's a reverse subtraction. Well, it's not really. Negation is so that you can say calculate 0 minus RZ, and so anyway, those are ordinary instructions on arithmetic on 64-bit numbers. But then there's also something that you sort of hide under the table unless you start working with the details of machines, and that is what happens if you add two numbers together and you get something that's too big, it doesn't fit in 64 bits. Well, overflow occurs, and so then you have to decide what are you going to do about overflow. You're going to ignore it? You're going to make it possible to see it somehow? And what do you do? Now, overflow is especially important not only for integer results but also for floating point results. And these instructions near the top here are floating point instructions like FADD, floating add, and it was important to be consistent with the IEEE standard on floating point, which is well defined and has been in existence for more than 10 years and has a heck of a lot of good ideas in it. So I knew that I was going to use IEEE floating point arithmetic in MMIX, and therefore, in order to keep this whole thing easy to learn and clean and so on, I had to make whatever rules I chose for fixed point would have to be the same as the rules for floating point. And so IEEE defines different kinds of exceptions that can occur on floating point arithmetic. Overflow can occur, underflow can occur. You can divide by 0. You can have a result that's not a number. You can have a result that's undefined, like square root of a negative number. You can have a result that's inexact. So they defined a whole bunch of exceptional conditions, and so whatever I did with floating point numbers, I would also do for the idea of an integer integer overflow. And so that is. Let me show you now something that. There's a web page that shows these opcodes, that's reachable from the other MMIX page. It says click here for the 256 opcodes and that same chart there. And then at the bottom of that page, it tells you about all other kinds of weird codes. And for example, the exception codes that we have are all listed here. The trip codes, the DVZ, IO, UZX. So integer divide check, integer overflow, and then the fixed point operations, floating overflow, and so on are these others that come from IEEE. W is a separate. I didn't know. IEEE didn't specify what. When you're converting a floating point number to a fixed point number, should it be an integer overflow that you get or a floating point overflow that you get? I decided to make a separate one for that, so that if you were interested in calling it one way, you could enable both of these. Otherwise, you do the other one. So I have 8, and besides, I needed eight codes to fill a byte. So it all packed real nice. So that's what happens if you add two numbers together and or subtract one, and the result is out of range. You get integer overflow, and then it depends on what the programmer wants, just as in floating point. So there's a separate register which says, do you want to do anything special? Do you want to interrupt your program on an integer overflow, or do you just want to sort of log the fact that it happened and go on? And that's handled the same way as with floating point. So actually, this if you do decide on interrupt that you're interested in it, it will go to one of your own routines like a trip that you write yourself, that you can write yourself, and you can in this handler it's set up so that not only can you say, oh, by the way, you just had an overflow on your instruction such and such. You can also correct. It can also correct the error and substitute another result if it wants. If it wants to do something. So the multiplication and division are in here somewhere. Here's multiplication. I put them up here because they tend to be slow instructions like. So maybe we combine the multiplier with the floating point multiplier in hardware. You could share a lot of stuff maybe. But multiply and divide again, they can overflow, and these instructions are all 64-bit to 64-bit. Now, however, there's also unsigned arithmetic, which never overflows, never has exceptions, and so you add the letter U. So add unsigned says we're doing like in the C language. If we have unsigned numbers, we just work mod 2 to 64. We just let carries go in and out the door, or whatever, at the left end, and so we got a lot of unsigned things where it says. I don't care if it overflows here, and don't ever interrupt on these guys. There's also negate unsigned, and now and the multiply and divide are unsigned are also nicer from the standpoint of doing if you're doing multiple precision arithmetic, because the unsigned multiply gives you 128-bit. Product instead of just 64-bit. If you want to look at the high order bits, and divide unsigned takes 128-bit in and produces a quotient and a remainder. While the ordinary divide does produce a remainder, but it doesn't. But it only starts with a 64-bit given. But in general, that's the idea. Now we got. Also, I got a whole bunch of little things like 2 add, unsigned. It says multiply by 2 and add, multiply by 4 and add, multiply by 8 and add, multiply by 16 and add. This is useful if you have to do subscripting and you want to move along by 2 bytes, 4 bytes, 8 bytes, and 16 bytes. And now I got to talk about multi-byte words. This is a little bit fun. We have bytes here. It's 8 bits equals 1 byte. Actually, let's go. Let me change that, because we had actually two nibbles is 1 byte. a lot of times people needed a word for like a hexadecimal digit, something that's four bits long, and it becomes one nibble, and then of course we have then the problem of making other names here, and I got a letter with a good suggestion from a guy who said 2 bits is 1 nip, and 2 nips is 1 nibble. Okay. Now there's a big need for a 16-bit quantity, and a lot of people have come up with different names for 16-bit things, but unfortunately there was the most common thing for 16-bit quantity is a word, and this is what I found even used. Intel considered 16-bit to be one word, and even though they go to, and even the alpha was talking about 16 bits as a word, and a 64-bit thing was a quad word to the alpha to the people there. On the other hand, when you grow up in the Unix world, everyone knows that a word is 32 bits, but for Cray, a word was 64 bits, and so it was quite clear that the word word had impossible to use in a way that you could get any agreement on whatsoever. And there were a few other proposals for 16-bit things, and I summarized all of them actually on a web page if you're interested, and I can refer to if you look at my News 98 page. It discusses it. But anyway, after thinking about it and talking over with a lot of people, I came up with the right answer, which has been spreading around the world very rapidly. 2 bytes is 1 wide. Now it sounds a little bit like word, just say with a Brooklyn accent. So if so it's okay. But it wants to very much to be a 1-syllable word that starts with W. And one of the big reasons for this is that the extended Unix now, the functions that use these 16-bit characters, Unicode is growing fast, and it's this code that handles all the essentially all the world's languages except Burmese, and because they haven't been able to get into Burma yet, but it'll handle Burma too, and so Unicode, the 16-bit code, all kind of subroutines are needed for things like wprintf, and wget_s and so on. All the Unix the C standard library functions that work on 8-bit characters, the corresponding ones for 6-bit characters have a W in them, and so it really is nice because this is the wide print version of the thing and so on. So 2 bytes is a wide, and I've been using this now for quite a few months, and in fact, not only it's been spreading so fast that Byte magazine ceased publication last year, and the successor to Byte has been named Wide, and it's going to be an online magazine. It's very interesting. And I did find that some conflicts, like was already a magazine called Canada Wide for large Canadians, but that's too bad. But they'll probably get a kick out of this. Now so 16-bit things, we call them wides, and it works. The next thing, though, what should I call the 32-bit and the 64-bit thing? And at this point, all these, I don't know, our memory is good at remembering a few small things, but after that, after thinking about it a long time, I realized that this kind of clever use of Y and stuff is not going to, it shouldn't continue on because it gets to be a difficult thing of memory after this point. So here I call it a tetrabyte or a tetra. You can say tetrabyte if it sounds better to have another syllable in the word. And 2 tetras is an octa, or octabyte. And it's because the more you look at programming these things, you have to somehow have a strong remembrance that 4 are associated with 32-bit words and 8 is associated with 64-bit words, because you have to realize that you're passing over that many bytes in the code. And whenever you're looking at a program, and if you have to stop and think, well, now how many bytes is that? Then that's wasted time. But if it's an octobyte, you know how many bytes it is. So anyway, these are the terms that MX uses, and I believe they're spreading one. So now yeah.
Why not dual then instead of, or something, or duo instead of?
Of why?
Why not begin the switch? If byte is the fundamental unit, why not begin the switch immediately? Too late, I know, but I'm just asking.
I kind of liked wide because, but you could maybe do. I think that was already copped by somebody in the. I mean, like I was thinking of octet, for example, but octet was out because octet is used by all the coding, the information theory community, and I so okay, so anyway, the instructions in MX here are load byte or load byte unsigned, or load wide, load tetra, load octa. Okay, and that means that you're taking out of memory either 1 byte, 2 bytes, 4 bytes, or 8 bytes. And load byte will also extend the sign. So you look at a byte is considered to be a number between minus 128 plus 127. And load byte is then brings the byte into a 64-bit register. Now I should mention that people say it's a reduced instruction set machine, but how can a machine with 256 opcodes be considered a reduced instruction set machine? And the reason is that in fact, if you look at the alpha and the power PC and stuff like that, and count the number of instructions. It's not 256 isn't out of line. In fact, the idea of reduced instruction set is not that there's a small number of instructions of opcodes, but it's a small number of different conventions in the opcodes. And really, the characteristic of the architecture is that the references to memory are confined to loading and storing from memory, and everything else is between registers. So it's sometimes called a load store architecture or a register architecture because actually all the instructions in the 8s, 9s, A and B here in these 4 bands are load and store to memory, while the other instructions in all the other bands are just between registers, and that's the idea of a Risc architecture. Now, in that case, the instruction is not that register X is set to a function of register Y and Z with an ordinary operation, but in this case it means you add register Y to register Z and then look in that memory location. And then you either load that into register X or store register X into that location. Or else if Z is an immediate, then you add this constant to the base register that's in register Y. So that's the idea of load byte. Load byte unsigned would be the same as loading a byte, but you don't sign extend it. You just put zeros into the other bytes. Load tetra unsigned, loads the lower 32 bits, but upper 32 bits goes to 0. Load wide unsigned. Now I have a load octobyte unsigned. It's exactly the same as a load octobyte, but as I said, I wanted this design to be orthogonal and consistent. So if you're dealing with something that I have there's something about this here. A foolish consistency is the hobgoblin of. Okay, so anyway, yeah, no, no. Anyway, there's reason to be consistent in design instead of I had this extra. I could have defined some fancy opcode in here, but it broke the pattern. I didn't want to do that. There's load short float. This is a floating point thing because the main thing I you find out when you have a 64-bit machine, single precision floating point, the 32-bit floating point numbers don't make any sense anymore. It's almost terrible to imagine computing with 32-bit floating point if you have a 64-bit register. Except that you might want to pack the data or get it from some program that was from long ago. So I can find so I don't have a single precision floating point addition, but I can load it into a register and I can add and then I can store it out again, and that's enough to actually round to exactly the IEEE standard. But I don't want to talk. Load high tetra is that you take a tetrabyte but you put it in the upper half instead of the lower half. And these other instructions are kind of weird. I'll go into them. So then all the load instructions have corresponding store instructions that go with them. Store byte unsigned, store wide unsigned tetra, and so on. Short float, high tetra. Convention is that actually an overflow can occur when you're storing. If you try to store a byte and the value of the register is not between minus 128 and plus 127, then integer overflow is signaled. But store byte unsigned just takes the byte and forgets about overflow and stuff. Store a constant is another one in here. You can set memory location to 0 or some small number instead of putting it in a register. Okay. So the load and store instructions are characteristic of Risc machines. That's the way memory gets in and out of registers. But that's a major operation and major part of the hardware because there's all kind of layers of caches between the memory and the registers in order to get efficiency. Now I'll go quickly through some of the other stuff. Here's these commands here. There's 4 set commands: set high, set medium high, medium low, and set low. And these instructions all take a wide, a 16-bit immediate value. So it's a wide immediate, and puts it into either the highest wide of the register, or the medium high, or medium low, or the low. And increment the highest wide or the medium high wide, or into the highest or the medium highest, and not. This means take away bits from these. And so here we have 16-bit immediate things, and with 4 of these instructions, you can build any 64-bit constant you want into a register. And it takes 4 instructions, which is twice 64 bits, because each instruction is 32 bits. Well, we got through those instructions. Now the branch instructions are here, and there's 8 of them. Branch negative, branch 0, branch positive, branch odd, and then the opposite: non-negative, non-zero, non-positive, and even. And then there's 2 versions of the branch, and then these branches are relative to the location. So if you say branch negative to self plus 4, that means you go ahead 4 instructions in the code. But if you want to go self minus 4, that's the backward version of the instruction. And in that case, it's like having an extra bit in the opcode, because then you give the complement. It would say, if you wanted to go to self minus 4, you would say branch negative backward. Well, the assembler does this for you, but so you just say branch negative self minus 4 or the symbolic name of that location. But in the hardware, branch negative backward would say then minus 4 is given in 2's complement form. So those are the 8 branch instructions. They're easy. You give it the name of a register, and then if that register is negative, you can branch forward or backward by the other 16 bits in the instruction. So that gives you a range of plus or minus 65K instructions. Then there's the probable branch negative form and so on. So these are the same as branch, except you give a hint saying, I think I'll probably branch. Well, the branch says, I think I probably won't branch. And then the hardware can use branch prediction mechanisms to refine this guess, but it uses this as the initial guess anyway, the first time you come to an instruction. You can avoid branching altogether with these CS and ZS instructions that occur here. This is conditional set if negative, conditional set if zero, or so on, or zero or set if negative. These instructions, the meaning of conditional set negative is this. It says if register Y is negative, then set register X to register Z. Otherwise, don't set anything. And so you can often avoid a branch instruction. It's much faster on modern machines to do these things. And the zero set is similar. It says if register Y is negative, then set register X to register Z. Otherwise, set register X to 0, which turns out to be even easier to implement. And it occurs in lots and lots of programs. Okay, the Boolean operations are real simple. The or and or with negative and with the negative or complement or not. And then there's nor and nan, which is the complement of or, exclusive or and not exclusive or. So these are 64-bit operations on bits. I should talk a little bit about the shifts here. This is shift left unsigned, shift right unsigned. One thing I'm a little bit worried about if my books have all these instructions I'm trying to define in such a way that they should have been defined on all the machines now, but I find that almost all machines define shift wrong. That for example, on a 32-bit machine, it'll only look at 5 bits of the amount of shift, and so it won't distinguish between shifting by 0 and shifting by 32. Which are rather dramatically different, in fact. And so compilers have to worry and have to test for this special case if they're going to implement the language with a variable length shift. So in my machine, a shift left is exactly equivalent to multiplying by a power of 2, including whether or not an overflow occurs. If you want to replace multiply by 16 with a shift left 4, it's absolutely legitimate in MMIX, but it isn't on other machines. So I'm afraid maybe readers of my books are going to program in the real world are going to assume that the real world is actually as nice as this. I don't know, but still I'm going to do it the right way in hopes that machines will eventually change over and they'll be in the majority. Shift left unsigned is the same as shift left, but no overflow occurring. So it's the same as multiplying by 16 unsigned. Shift right, again, is equivalent to dividing by a power of 2 in all cases. And with the sign extended in the arithmetic shift, the unsigned shift brings in zeros from the left. So these instructions are fairly easy to understand. I got a Mux instruction here. This is multiplex instruction, which says register X is set to either register Y or register Z, and each bit position is determined by a mask, which is in another auxiliary register. So you have that fancy instruction there. Let's see. To make comparisons, you have less than unsigned, equal unsigned. Equal unsigned is the same as equal. But you compare one register to another, and then you set it to 0 or 1 based on whether the thing is less. So anyway, a lot of these instructions are easy. The jump instruction is trivial. That's an absolute jump. Here we have it's relative with XYZ, all treated as a 24-bit constant, so you can jump plus or minus 2 to the 24th instructions. D jump is the same, but it's dynamic. It's for like a case statement in C, where you want to do a switch statement in C. And the get address is saying put into a register the address relative to your present location. So this saves you means that MMIX programs can pretty much be loaded into any part of memory without the loader having to relocate a bunch of stuff. The families of instruction I've talked about, then we had arithmetic, and we had Boolean, we had load and store, we had branching, and I haven't talked about floating point. That actually takes a while. so I can just say quickly, it's quite analogous to everything else we've been saying. I have comparison instruction, floating point less than, floating point unordered with respect to, these are things that you need for the IEEE standard. Convert from fixed point to floating point, convert from floating point to fixed point. All of these things are fairly fairly straightforward, but I want to talk about some of the other more interesting parts of the machine. So there are two innovations I want to talk about. One very briefly, and the other one at a little bit slightly more length. The one I want to talk about very briefly is the instruction called more, and there's MXOR as well. Now, this is an instruction that doesn't exist in any computer right now. So why should I put it in a machine if it's supposed to be realistic and so on? Well, it's because it's ahead of time. In fact, I think there was a machine something like this in the microunity machine that never saw the light of day. In fact, these instructions are much simpler and cleaner than instructions that are going into a lot of machines now to do what they call multimedia or operations. Anyway, there's a lot of special hardware going in to facilitate operations on pixels and stuff like that. And I have also instructions called byte diff and wide diff, which work on parts of words simultaneously. So, for example, you can be subtracting all the bytes of two different registers, but each byte independently without carrying into the next, and replace it by 0 if the result is negative. These instructions have actually become known in Intel world as MMIX technology. I can claim having the word MMIX before they had MMIX technology because I gave this lecture in 1992. But anyway, it's just an interesting coincidence that their MMX technology is for instructions like this byte diff and wide diff. But the more instruction is based on the fact that 64 is actually 8 times 8, and when you have a 64-bit word, it's natural to actually think of that word as if it was a matrix of 8 rows and 8 columns of bits. And then you can say, well, so sometimes a 64-bit word represents an integer. Sometimes it represents a floating point number. But here it also can represent a matrix. And so this means multiply matrices. Multiply the registers together as if they were 8 by 8 matrices. And MXOR is the same. Multiply. There's two ways to calculate the product of 8 by 8 Boolean matrices. One is by taking the OR, and one is by taking the exclusive OR of the things as you're going. Let me just explain. For example, if you multiply by the identity matrix, you don't change anything. But if you multiply by a matrix that looks like this, you flip the bytes from left to right. So you go big endian to little endian. Okay. If you multiply by this matrix on both left and right, you flip all the bits. This is but in general, if you multiply by any permutation matrix, and if you multiply by the permutation matrix on the left, you're permuting the bytes of the word. If you're multiplying by that permutation matrix on the right, you're permuting the bits within a byte. If you have several ones in a row, then you're putting several bytes together. I give in the write-up, I give a whole bunch of applications of this to show how you can do lots of stuff with just a few instructions, and it combines nicely with the other things like the count bits instruction. And Dick Seitz told me that every computer architect is entitled to have at least one instruction that's going to look silly in 10 years. And so maybe this will be it, But I think it actually is going to catch on, but who knows? You couldn't use it in C compiler would never use it unless you build in something where a person could define a data type to be an 8 by 8 bit matrix. But you can use these things also for efficient calculation in finite fields. I don't know. I couldn't resist putting it in. Now the other thing I want to tell you about is the subroutine linkage in the machine. Subroutine calls stack or a register stack. This if you look at what actually happens in the programs that are being run all the time. Now a significant amount of time is being spent taking arguments, getting arguments into subroutines and getting parameters into subroutines and so on, and passing the results back out of the subroutine. And so people realize this, and they design different architectures in order to make the passing of arguments and so on reasonably fast. And it has to work with recursive subroutines and all kinds of stuff. There are various solutions to this, and the one that came out of Berkeley Risc is now on the Spark is the idea of Windows. This has nothing to do with Microsoft. But this is a separate bank of registers that you move around when you go into a subroutine, and you get to look at the some registers in common between caller and callee. And then the other case is where you pass the arguments in registers with other conventions. Now. Each of these has its champions and has its pluses and minuses, but I have something that I think is a nice compromise. It sort of does. You can do it either way depending on your own preference, and it's too difficult to explain real quick. But so I have to just give you the highlights. But here's the idea. I said I had 256 registers. But I divide them into local and global. So let's consider these are all the registers here, and I have a pointer G. It says everything greater than or equal to G is global. So G is the max of G is 255. So that would say you always have at least one global register. So these registers are global. Then I have another register L that says everything less than L is local. And everything between L and G is 0. Now, so this ties in with something I said before, that if you're storing the context of a program, you don't have to store all 256 registers. You only have to store the locals and the globals, and not all the zeros in between. So if somebody isn't using these, it's okay. But if somebody says add. And one of the registers that you're adding is in this marginal region between L and G here. Well, it just reads as if it's 0. If you try to store into this register, then L silently moves up. You don't have to know what L is. It'll just the idea is the programmer should use the small numbered registers whenever possible. But if you have an instruction and the instruction says add register 100 to register 200 and put it in register 20. Well, register 100 and 200, they might be local or global depending on the value of G. But I have to tell you something else that's different about local and global. Otherwise, its concept wouldn't make that much sense. And so the other part of the idea is that in fact these local registers aren't sitting in a linear array like this, but actually the local registers are sitting in a circle that has an arbitrary offset, and register 0 through register L are actually sitting somewhere in this circle. When I go into a subroutine, I can push I have an instruction called push go, which says push down a certain number of your registers and go into the subroutine. So if I push them down, it essentially says that the offset is here, and L has just decreased by that amount. So if I say push go by 10, L has just gotten 10 less, and I push down 10 of my local registers. Now the subroutine can start using its own local registers, adding to this if it wants to, but it's got all these arguments that are still in there that are passed. It can put its answers in here, and then it can say pop, and it can say pop 5, which means leave 5 of my local registers, and then go back and take all the ones that you push when you went into me. So that's now the idea is that even though I said push 10, the machine only had to change this offset. And as you issue the instructions, you add the offset to the local registers, but not to the global registers, and you get the local registers out of this ring, while the global registers come out of another array. And so, if you're interested in the details, it's all described in this document that's on the web. But the basic idea is something like this: if you say, if you like the Spark-like windows, then you would say push go 8 and pop 8 when you more or less it is subroutine linkage. If you like the MIPS type of thing, you would say push go infinity and pop 0, which infinity really means push go all of your locals and pop and remove them all on popping. More or less that's the same, and then they have a certain number of global places for communication. But the idea here is that this scheme adapts itself to whatever the needs are. If you have a subroutine that wants lots of locals, okay, it's got them. If not, it doesn't. If you have an application that wants lots of globals, you can have a low small value of G. If you have an application with lots of locals, you can let it grow this way. And that's the idea of late binding, not the architect design in advance what's going to be right for all programs, but let the programs do this. Now I had to implement my simulator to make sure that this idea would work. That you could do it with a pipeline and not lose too much. And of course, there is extra hardware involved in adding this offset in here and keeping track also automatically of when you have to store things in memory. You start wrapping around the circle. You have to dump things out into memory and load them back in again. But I've got that all worked out, and I think it's the amount of hardware is reasonable considering the trends in technology. It gives you something good, I think, reasonable to do with silicon, because I think the effect that you're going to get for saving running time on calling and going in and out of subroutines, combined with the compactness that you get of having a large number of registers in a program is a win. Anyway, I decided that this was going to be the subroutine. The subroutine calling mechanism recommended in my books, although another style of subroutine linkage can also be programmed with the other instructions. Well, it takes always a long time to explain these things, and in this write-up. There's some. I also went into the things that are the messy details that are needed, all the instructions that are needed by the operating system in order to do its, in order to, for example, get things in and out of different caches and to handle virtual addressing to physical addressing, and what happens on interrupts, and how do you restore and save unsaved context and things like that. There's MMIX has 32 special registers that are used. Each has a number from 0 to 31, and I told you about the multiplex mask register, for example. But there are other registers for the high half of the product and things like this. So all those details are there, not really needed for unless you're going to write the operating system for some of the weirder ones. I'm left a little bit wondering about this easy to learn part. What if I have to look at the entire document and say you're going to learn all of the instructions that are there in order to handle the full complexities of operating system. But I still needed those instructions in order to make the thing complete, and I'm going to have those separated out into special reference books and not in the main text. So in general, I have to say that I hope you all like it as much as I do. I can't wait till I own one of these machines, and I'm actively looking for volunteers to help with the job of translating all of the programs that were done in MIX into MMIX. For this purpose, I've got a wonderful helper, Vladimir Ivanovich. Vlad, are you here? Stand up, please. So, and he has just he's just setting up the homepage for MMIX Masters, which will be the volunteer group, and this is www.mmixmasters.org, and it is going to he's going to help organize, so people will choose the parts that they're going to work on, and all the information is here. Furthermore, in the next few weeks, I'm going to be making a lot of decisions about the assembly language that, and I would very much like to have a group of people that we would shoot the breeze about these ideas for 2 or 3 hours, and see, knock down my proposals for December, before I spend too much time writing up something that people aren't going to like. This is what we did when Tech was designed. Every Friday for about 4 years, we had a meeting of 2 or 3 hours of anybody could drop in, and we would discuss aspects of Tech, and I'm looking forward for having 2 or 3 meetings to talk about ideas of MMIX in March. If any of you are interested in participating in these, we could talk after this right now, and then after my lecture in March, on March 3rd, and we'll try to set times that'll work for people. Because I really would appreciate this chance for feedback on some of the trade-offs designing the assembly language. The architecture itself is fairly close to is getting to the point where it's pretty much hard to change now, but still not too late to make a change if you've got a really great improvement on what I have. Okay, any questions?
Does the overflow of unsigned shift left affect high mark register?
No, unsigned shift left does not overflow. But the unsigned shift left does not go into the high mult. No. You think it should? It could. Yeah. No. It would be. It'd probably be a good idea. I hadn't thought about that. We could. Yeah. We have to. That's a good suggestion. Because high mult is affected right now by only the multiply unsigned, and so I could make it exactly equivalent. And yeah, I had this idea that if I wouldn't have just 1 or 2 auxiliary registers, having only 1 or 2 auxiliary registers means there's a lot of competition for them in the pipeline. So a register that's used for the upper half of a multiplication is different from the one that's used for the upper half of a dividend. But here is a case where it's quite natural for 2 instructions to use the high multi register. Very good. Yes.
Did you consider bit addressing or byte addressing?
No. No. Burroughs tried that in the 60s, and it was just, that's too radical. Would you prefer that? I mean, it would. Yeah, I do. That's true. Yeah, that's true. In fact, I even consider decimal arithmetic. I mean, computers are getting so fast now. It might be that time them to make them human friendly again. But I rejected it. I think Java should probably have been decimal though. I mean, in its floating point. The biggest mistake in TeX was that I made it binary. I mean, internally, TeX works in units of 2 to the minus 16th points, and I should have had it be 10 to the minus 5th points, because then the thing that's printed when it says how many points it is would be exactly what's inside the computer. Right now, it's a rounded approximation. So there are aspects of decimal arithmetic that are better for human interaction. But I guess binary computers are still here for another 10 years. Anyway, yeah.
There's an issue with 256 registers. There's a lot of registers.
Yes.
And it's possible that the sort of things you might want to do in registers is different if you've got 200.
Yeah.
It might be worth putting an array in registers.
Yes, that was. Now, I should have mentioned that this was done in the Risc Architecture, the Hobbit, that right now my register stack, when I push things down, it's only scalars that I can push. I can't address registers. That's extremely complicated in the pipeline. So I rejected it at the moment. But your point is well taken. That we use them in different ways. And for example, I have banks of registers. Okay. The main loss that I have by having this many registers is that the immediate fields are only 8 bits. Hennessy and Patterson gave statistics of how large in lots of programs the immediate fields wanted to be, and you could get I don't know, 75% of all immediates would fit in 8 bits, but you could get up, if you could get up to 10 bits, then you would hit 95, 96% or something of all instructions would fit in a 10-bit immediate. Something like that it was, and here I am, with my nice one byte for each part of the word, having only 8 bits left for the immediate, so a base register plus an 8-bit offset. However, I can divide my base registers into groups of 4, so that it's actually have a 10-bit offset, because the lower 2 bits identify which base register in the bank of 4 there are. So if I have several things going off of one base register, I can actually have 4 or 8 base registers grouped together based on the context, and that's another example of how in fact there is an array of base registers, and here the assembler will even allow you to carry in. So if you have if you wanted to have an immediate field that's more than 8 bits, it'll actually carry into the number of the register, but then the loading routine will have set up those registers to differ from each other by 256. Yeah.
On that point particularly, many of the operands for, say, and or immediate, logical immediates, will have a lot of leading ones, and it'd be nice to have a
well, that's why I have the negatives of these instructions too, and I have the wide instructions. I have the, yeah. Yeah, we can talk offline about this, but yeah.
Does the increment family set the overflow?
The increment is unsigned.
The immediate part is the least significant byte?
What? Excuse me?
The immediate part is the least significant byte in the 64-bit word?
The immediate is always a low byte. Except when I say a medium high immediate, the instruction, like the set, I had a set high, set medium high, set, and those were 16-bit immediates. That's there's lots of when you go to 64-bit, a lot of problems get harder than they were in the 32-bit world, because you could more easily build a 32-bit constant than you can a 64-bit. But the most significant problem on a 64-bit machine was actually the virtual address to physical address problem that I didn't get into. because all the schemes that are used on 32-bit machines fail to scale up very well when you try to. I mean, like the ideas of page tables, which work nicely with 32-bit. I had to work very hard in order to have something that would be reasonable way to do the mapping for all conceivable changes in technology coming up. And I think I have a good compromise, but it's not simple, unfortunately. It's hidden from essentially all users, but still that was perhaps the most difficult 64-bit problem I faced.
Is MMIX like octobyte aligned or terabyte aligned?
So everything is aligned. Every command is automatically aligned, and
I can load octobyte from arbitrary address.
no, if you do, yes, you can, but it just ignores the low 3 bits. In fact, those low 3 bits are very valuable. There's a tremendous number of data structures where you want a pointer plus 1 bit or pointer plus 2 bits and so on, and you can use the low. The pointers you've got those bits right there, and it's totally ignored. Now, but I know that that there's it was necessary for the alpha to have instructions that allow unaligned loads, just because of legacy code. But fortunately, I don't have any legacy code. So I can design the thing to be right. And this multiply instruction, there's a short routine. We'll do the right thing with unaligned load. And then you do a couple of these more instructions on it, and it will shift the bytes into the position that you want and get it. So it's a fairly short loop to do unaligned loads, but I'm not going to. But I'm saying that a sensible program that starts out and doesn't have to worry about legacy, everything is always aligned. Okay.
You think of putting in a max instruction?
A max instruction?
Maximum.
Yes. Let's see. Well, it needs 2 instructions, but you got the compare. You got the compare and set if less, and so you can subtract and then you do a compare and set if less.
Does that imply a branch?
No, that's the point. Yeah. And there's also maximum and minimum on each byte, which you can do in 2 instructions. You take the byte difference and then you do. Let's see, and then you add in, the max is equal to the max of x and y is equal to the x minus y flushed to 0 plus y plus. Sorry, that's the min, and the max is similar, but you subtract. So max and min on individual bytes are there in 2 instructions as well. Okay, well, I guess time is up, and I'll be glad to answer other questions.